What if I told you there's one super simple rule that basically decides the shape of everything? I'm talking about the water you drink, the air you breathe, even the DNA in your cells. We're going to break it down right now.
So, have you ever wondered how your body knows the difference between, say, a Tylenol and a vitamin? How does it know what to do with a hormone? Or how do you even smell a flower?
Well, here's the big secret. It's all about shape. Yeah, at the tiniest molecular level, shape is literally everything. It's the language your body uses to talk to itself.
Okay, so how does this work?
Just imagine your body is covered in trillions and trillions of tiny microscopic locks.
Now, molecules like medicines or hormones, those are the keys. They just float around until they bump into a cell receptor that has the exact right shape. If the key fits the lock, bam, a signal gets sent. If it doesn't fit, nothing happens. It is just that specific.
So the big question is, what makes these molecules fold into these very specific, all-important shapes? Well, it turns out it's a beautifully simple idea. You know how people on a crowded subway kind of push away from each other? Electrons do the exact same thing.
The official name is VSEPR theory, which stands for Valence Shell Electron-Pair Repulsion. It sounds complicated, I know, but just forget the name. The idea is so simple. Electron groups are all negative, right? And negatives repel each other. So they just automatically push each other as far apart as they can possibly get.
My favorite analogy for this is balloons. If you tie a few balloons together at their knots, they don't just flop around randomly. Nope. They instantly snap into a very specific, predictable shape to give each balloon as much elbow room as possible. Molecules do the same thing.
And this one simple rule of repulsion, of just wanting personal space, gives us a small handful of basic, totally predictable geometric shapes. These are the building blocks for pretty much every molecule out there.
Let's do a quick rundown. Got two electron groups? The furthest they can get is 180 degrees apart. Boom, you get a perfectly straight linear molecule.
Okay, what if you have three? Well, the best they can do is arrange themselves into a flat triangle, kind of like a peace sign, with 120 degrees between each one. We call that trigonal planar.
And four groups, this is where it gets really cool. You might think they'd form a flat square, right? 90-degree angles. But no, to get even more space, they pop out into 3 dimensions to form a tetrahedron. The angle is a very specific 109.5 degrees. This is the shape of methane, which is a huge deal in organic chemistry.
All right, that seems pretty straightforward. But here comes the plot twist. What happens when some of those electron groups aren't actually forming a bond between two atoms? What if they're just hanging out by themselves as lone pairs?
This is where the really interesting shapes come from. Lone pairs, you can think of them as the bullies of the molecular world. Since they aren't stuck between two atoms, they take up way more space and they have a much stronger push. They repel everything else with extra force.
Let's compare methane and water. They both have a central atom with 4 electron groups around it. But in methane, they're all identical bonds, so you get that perfect 109.5-degree tetrahedron. In water, though, 2 of those groups are bully lone pairs. They push the other 2 bonds closer together, squishing that angle down to 104.5 degrees and giving water its famous bent shape.
You can really see it here. Those 2 lone pairs just dominate the space around the oxygen atom. And that powerful push is exactly what gives water all of its unique, life-sustaining properties. It's all because of those 2 bullies.
Now, VSEPR theory is an amazing tool. It's incredibly powerful for predicting shapes. But, we have to remember it is a simplified model. It works like a charm most of the time, but the real world can sometimes throw a curveball.
For example, take a look at phosphine, pH 3. Based on a similar molecule like ammonia, VSEPR would predict an angle of about 107 degrees. But in reality, it's way smaller, only 94 degrees. It's just a good reminder that our models are fantastic guides, but they're not perfect laws.
So if you ever want to figure out a molecule shape, it's just 3 simple steps. 1. Count up all the electron groups around the central atom. That means bonds and lone pairs. 2. Arrange them so they're as far apart as possible, just like those balloons. And 3. Name the final shape based only on where the atoms are. You just ignore the lone pairs for the final name. That's the whole game. So a drug hitting its target, the shape of DNA, the reason water acts the way it does, it all comes back to electrons just wanting some personal space. It's pretty wild that one fundamental principle can create all the amazing complexity we see in the world. It really makes you wonder, right? What other simple rules are out there running the whole show?